solar flares and CMEs are all driven by magnetic reconnection. This is where the sun churns up the magnetic field that's inherent in it, and then it causes oppositely directed magnetic fields to then annihilate. But you can't just get rid of magnetic field. You can't just get rid of energy. You have to convert that energy and transfer that energy into other things, such as plasma motions, accelerating the plasma, heating up the plasma, and also giving out more light.
We are protected here on the surface of the Earth from solar flares and coronal mass ejections when they impact the Earth due to the magnetic field of the Earth called the magnetosphere, which deflects the magnetic field and the energetic particles, as well as the atmosphere, which absorbs the higher levels of radiation.
But this magnetic field of the Earth also protects us from these charged particles, the plasma coming from coronal mass ejections. It largely deflects a lot of this direct energy.
The phenomenon of magnetic reconnection is not well understood. So NASA has launched a multi-satellite mission called MMS to try to unlock the secrets of our magnetic field.
The MMS mission is a mission consisting of 4 spacecraft which will fly in close constellation to measure a process called magnetic reconnection.
The universe is full of plasma and it's full of magnetic fields, and all over the place in the universe you have one plasma colliding with another. An example of that is the solar wind coming in and colliding with Earth's magnetosphere. And then the magnetic energy in the plasma, some fraction of that magnetic energy is converted very rapidly into plasma energy. So you can think of it as kind of like a magnetic explosion. And the reason this is important is because these explosions drive a lot of the weather patterns that we see in the magnetosphere, and so what space scientists like to refer to as space weather. And these space weather phenomena can have impact on our everyday lives. It can actually affect communication satellites, the power grid. So we'd really like to understand how these magnetic explosions work.
We need to measure reconnection in more than one location. We need to measure it in basically how it varies in space, how it varies in all 3 spatial dimensions. And that requires a tetrahedron. The additional fantastic benefit that provides is that it will actually enable us to recognize that we're looking with a reconnecting region much easier than a single spacecraft.
The ideal situation is that we would like the 4 spacecraft to kind of be surrounding this region where the explosion is happening. So the separation of the spacecraft is about 10 to 100 kilometers, which may seem like a long distance. But in terms of the magnetosphere, which is absolutely huge, this is really a microscopic region that we're trying to cover.
MMS has, in a nutshell, 2 orbital phases which are designed to study reconnection.
On the day side, basically you have a situation where the solar wind is just constantly running into Earth's magnetic field. And this is really great for MMS because we know that at some point MMS is going to encounter this region, and our hope is that since this process is always happening, we're going to get lucky and actually fly right through the magnetic explosion as it's happening. Now on the night side, the situation is a little bit different. So what happens is you have a more gradual buildup of magnetic energy in the tail, and these reconnection processes, these magnetic explosions, can just sort of pop off randomly. We don't really know when it's going to happen or where it's going to happen in the tail.
We need to understand both of those if we want to understand how the magnetosphere works, and we believe that both of those scenarios are also very important for other applications, such as on the sun, in the solar wind, in planetary magnetospheres, and in many astrophysical objects, as well as in the laboratory.
We hope that it's going to allow us to improve our models so that we can put the right physics in it and actually make predictions about where and when reconnection is going to happen, and this will help us make our space weather models more predictively powerful. The instruments that are actually going to be measuring the particles in space are collecting them much more rapidly at a much higher cadence than they have on previous missions, about a factor of 100. So whereas it would take a previous generation particle instrument about 3 or 4 seconds to build up the whole picture of the sky, it's going to take MMS about 30 milliseconds. So it really is sort of game-changing technology.
The current 24 or so operating satellites will be enhanced with new missions under development. The Japanese Space Agency will be launching their next solar physics satellite, Solar C. The Indian Space Agency will be launching Aditya to study the Sun's coronal mass ejections and magnetic field structures. The Deep Space Climate Observatory will maintain real-time solar wind monitoring capabilities critical to the accuracy and lead time of space weather alerts and forecasts. The European Space Agency's solar orbiter will be launched in 2018 and fly closer to the Sun than the planet Mercury to study how the Sun creates and controls its heliosphere. Also planned for a 2018 launch is NASA's Solar Probe Plus. It will approach the Sun more closely than any other probe before, at just 3.8 million miles from the surface of the star. Scientists have long wanted to send a probe through the Sun's outer atmosphere. The spacecraft will be exposed to temperatures approaching 1,370 degrees Celsius. Together, they will continue to monitor, study, and discover the secrets of this nuclear anvil that supplies us with light and life. Aside from the science, the images captured reveal to us the beauty and power of this, our nearest star, in all its grandeur.